Okay, let's get started. Good morning, everyone. Welcome back. So last time we visited the local power plant, the only power plant in Seoul, and the first power plant in Korea historically, and the world first city underground power plant. So yeah, that was an awesome experience, and I'm advertising my experience to other people, including the professors in our departments. Okay, so now you know what's going on in the generation company, and it is a good time to talk about participating in electricity markets. Okay, so in chapter 2 we discussed the general things about economics, especially from microeconomics perspective. Chapter 3 we talked about the organization of electricity markets, and in chapter 4 there are 3 types of market participants. So the first one is generator, second one is consumer, third one is retailer. So we visit one by one, starting from consumer. Okay. So participating in electricity markets, the consumer's perspective. That's the first topic. So yeah, consumer's perspective, just one page. So you are consumers, and I'm also a consumer, and of course we want to apply microeconomic theory, and there was a concept VOLL, or called VOL. Well, we will discuss this maybe in chapter 6 more detailedly, but what VOL stands for: value of lost load. So VOL is the amount you are willing to pay to avoid outage, right? So normally this price is much higher than the normal electricity price, maybe more than 100 times. Okay, so because the interruption or outage of the facility is pretty bad for manufacturing company, for example, Samsung Semiconductor, they want to avoid the interruption or the outage of the facility. So they are willing to pay some money, much more money, for example, 100 times more money than the normal electricity price. And so this is from a large consumer's perspective. You are not this kind of consumer. I think you are kind of okay, or maybe even happier than in normal case when power outage happens, right? You can turn on the candle and enjoy the nice mood in the evening, for example. But from industrial perspective, that's not the case. And yeah, so different types of consumers: industrial consumers, residential consumers, and building consumers. So this is especially important for industrial consumers. And from microeconomic perspective, well, it assumes many things for mathematical analysis. And one of that is to assume that each consumer is rational. Okay, rational means they want to maximize their utility, right? And utility minus the payment or cost. So they want to maximize their net utility. So that is called utility maximization. Utility maximization is a common term in microeconomics. So the people try to estimate the utility curve, especially in power electronics. People try to estimate this utility curve as a function of the power consumption. Okay, so assumption 1, utility increases as you spend more power. You can operate air conditioner, you can operate heater, you can cook, you can watch TV, etc. So yeah, the utility increases as the power consumption increases. The second assumption is that the marginal utility decreases. in power consumption. Okay? Utility increases in power consumption, but marginal utility, what did I say? Marginal utility decreases in power consumption. Okay, so combine these two things together gives you the concave increasing function of utility, right? So typically we assume utility is a concave increasing function. And one of the good example is the log utility. Log is a concave function. So log is a very popular utility function, and if you take the derivative of log function, you have this kind of decaying function. So marginal utility decreases. Good example, good for mathematical analysis. Or you may want to use quadratic function, minus x squared, blah, blah, blah stuff, okay? So then you may want to use, if you have this kind of quadratic function, you may want to use only this portion, the increasing part, and the marginal, the derivative of the function decreases. Okay, actually that was the assumption used in Hing's paper. Hing, you know what I'm saying? Yes. Yeah. So as long as we have that kind of utility function, then we can define, we can analyze the price elasticity of demand. What it says is when price changes, how much you are willing to increase or decrease your power consumption. Okay, so that was called price elasticity. As the price changes, when the price goes down, you may want to increase your power consumption, and vice versa. And the question is, how much does your power consumption changes in proportional to the price change? Obviously, the direction is opposite. When price goes up, your power consumption decreases, and vice versa. But how much does it change? And we know that the price elasticity of the demand or load is very low. It's almost not changed. The reason is because power consumption is very essential for our life. Okay, so even if price goes up, you may don't want to turn off your air conditioner, or you want to watch TV, etc. So very, very low price elasticity. But anyway, these days, reducing power consumption is equal to increasing power generation. So during the time when there is a power shortage, then we are thinking of demand reduction as a demand response program. So we talked about this many times before. Or you can shift your demand. If the price during the midday, if the price is very high, you can shift your load to morning or in the evening when the price is low. For example, you can run your laundry machine either morning or in the afternoon when the price is low. Okay, that is called power demand shifting. And to do this, you may want to use energy storage, home energy storage, home ESS. And yeah, we are already having the commercially available home energy storage made from Tesla or LG, etc. So they want to have some algorithm to automatically operate the kind of home ESS, right? So we are about to do that now. Yeah, I'm about to sign a contract. Okay, so that's consumer's perspective. And let's talk about the retailer's perspective. What is retailer? So we have a wholesale market. In wholesale markets, generating companies sell their electricity. But they cannot sell this electricity directly to the consumers. Okay? Consumers buy electricity from retail company. Okay? So retailers buy power, energy from the generating company and sell it to the consumers. So there should be the price difference, buying at this price and selling at that price to the consumers. So this difference is the margin and the profit of retailer. Okay. So sell energy to consumers mostly at a flat rate. Price, they are used interchangeably. So yeah, actually, in Korea, you as a residential customers, you are using a flat rate, but this flat rate changes in accordance with the total amount of your energy consumption. Anyway, so this retailer buy energy in bulk in a wholesale market using a forward contract, including day-ahead market. Okay, and also this retailer can transact energy in spot market. Why do they need to transact energy in spot market? Retailer, why? You see what I'm saying? Do you understand my question? So yeah, this is okay. They need to purchase, they need to make a contract in advance in forward market. But then what about spot market? Anyway, there will be an imbalance on that day, on that time. Okay, so if energy is in short, they need to purchase power from spot market and deliver it to the customers. Or if they overestimate the load and overbuy the energy, then they can sell it in the spot market using the spot price. So that's why this retailer should be good at load forecasting. Okay, they need to buy energy in bulk in advance based on their load forecasting, right? So the load forecasting error is directly impacts on their profit, right? And so in doing this, yeah, if this retailer is a regional monopoly, then they are in a good position. That means, there is only a single retailer in this wide region. That means total load in this region is pretty huge. Then the load forecasting is easier. Just 1% or 2% of load forecasting error can be achievable for Korea, for example. But yeah, so in Korea we have a single retailer, KEPCO. But no, that's not always the case. When you look at the Japan, so today morning I sent you an article that's about the liberalization of electricity market, especially from retailers' perspective. Okay, so in Japan, 2016, this resale market was liberalized. So not anymore a monopoly, but there are a lot of retailers, maybe more than 100, 200, 300. Check it. Okay, so in that case, a single retailer only covers a small region. So the load fluctuation would be a lot, right? So forecasting is harder. And also, a lot of retailers means that from consumers' perspective, so what does that imply? You live in Tokyo, for example. Then you have an option to choose a retailer out of many. Okay? And then, in terms of about wireless communications, you can choose SKT, KT, LG Plus. Similarly, in this power electricity market, you can choose retailer A, B, C, D. Okay, so then the customers can move around. They can change their retailer from time to time. So that is called churning. Okay, the user churning. So this retailer, okay, they only covers a small region, and so load forecasting is hard. And also the customers can change, can switch to other retailers So the problem is more challenging. Okay? So, yeah, anyway, that's the beauty of competition. Okay? And the efficient retailer would survive. The efficient retailer means that who has a very nice, good technique to forecast load and manage customers and provide better services. Okay. So we will see several examples. So this is about load forecast, this blue bar. And this is the price, the forward price at which this retailer buys energy in the forward market or wholesale market. Okay, so obviously, this forward price changes. This is maybe a SMP, for example. Okay, so this is an hour. We have a 12 time slots, 1 hour period. Anyway, but the basic rate is the flat rate, retailer rate. So here in this example, okay, this is the energy, so megawatt hour, and this is the dollar per megawatt hour. So $37, I guess, the flat rate. So in this reason, this retailer cannot make a profit, or can make profit, sorry. So they are making profit in this reason. They are selling energy higher than their purchasing price. But during this reason, they are at a loss. So this is that figure. Cost of forward purchases, that is this orange one. So this cost is just the this forward price times the forecasted load. Okay, so that's the cost, and this is the revenue. So this is the real load times the flat rate. Okay, so can make profit here, but they lose money during daytime. So this table is the summary for 12 hour 1 to hour 12, and this is the load forecast, this much. Okay? And based on their load forecast, they purchase energy in this forward market. So they are same actually. Okay? And this average forward price, this is determined by someone else. This is determined in the market. This can be SMP anyway. So this forward price, average forward price changes over time. So this is same to this one. Am I correct? So 28 something, 24, yeah, blah, blah, blah. And the cost of forward purchase is just this times that. That gives you this number. And hourly revenue is the flat rate times the load. And here we assume that load forecasting is perfect. Okay, so flat rate times this load gives you that. So revenue minus cost give you the hourly profit. So profitable, non-profitable, profitable, and so on. So here we assume just a flat rate or tariff. Yeah, rate, tariff, they are used interchangeably. And in this example, we have two different types of tariff. So off-peak retail rate and on-peak retail rate. So, you can imagine why this price should be different. Why should they be different? Yeah, during this on-peak period, there are more load, and they want to reduce this load. But here, in this period, they cannot make profit. Actually, the cost is greater than this revenue, so they want to increase the price. Yeah, on peak retail rate is higher than 37. So in this simple example, this is 38 and this is $36 per megawatt hour. Yeah. So obviously, if you compare this figure 4.2 and figure 4.4, this hourly revenue is increased in this region and decreased in this region. But anyway, the load during this day is higher than the off-peak hour, even though the average price is same, but they would have more profit, right? So that is here. Retail operations over a 12-hour period for an on-peak retail rate of $38 per megawatt hour and an off-peak retail rate of $36 per megawatt hour. So is it same example? Different example actually. So yeah, load forecast, forward purchase amount are same, and average forward price, this is determined by same. 1, 2, 3, 4, 5. Yeah, this price is same as in the previous example. So cost of forward purchase, price times the quantity gives you this number, and the revenue is different time, different rate. Anyway, the price times quantity gives you this revenue. So revenue minus cost gives you the profit. So anyway, the total profit is positive here, but in previous case, the profit is negative. Okay? Anyway, so yeah, flat rate versus off-peak or on-peak rate. But so far we assume that load forecasting is perfect. But no, forecasting inevitably has error. So that's why we have imbalance. Okay, so this figure shows the imbalance between the forward purchase and actual energy consumption. So in this figure, again, we have a 12 time slots, and this is a megawatt hour. So this positive means energy shortage. So this amount of energy, more than 50 megawatt hour, should be purchased at spot market by paying the spot price and need to be delivered to the customers. Okay, so this is the amount in shortage, and this black line is the cost. So spot price times this volume gives this money. Okay, so what it says is the load forecasting during the day was inaccurate, actually under forecast, and there were more load than estimated, than predicted. Okay. So the energy deficit must be compensated by buying energy from the spot market. But in this period, the load forecasting was pretty bad. Okay, yeah. But for this case, there was an energy surplus, and that can be sold at the spot market, at the spot price. So actually, this is the benefit, this is the profit, this is the cost. But anyway, sum of all of this gives you a negative number. That means imbalancing cost occurs in this example. So all of these figures and example, the scenario is in your textbook. So if you need, please check your textbook. So this figure shows the spot price. We don't know how the spot price are determined, but this is determined in the spot market, okay, based on the amount of imbalance and based on the capability of other producers at the time and based on the total mismatched demand at the time, right? So based on the demand and supply on the spot, on that day, on the time, and this spot price is anyway determined. And in this case, it is higher than the average forward price. So when there is a energy deficit in this time duration, the retailer need to purchase that amount of power by paying this price. So that incurs a huge loss to a retailer. Yeah, so this table, retail operations over a 12-hour period for flat rate of $37 per megawatt hour, considering forecasting errors and implied spot market trades. So this is the load forecast. And forward energy purchase. Yeah, so this forward energy purchase is totally based on the load forecasting. So they are same. And this is the average forward price. This is same as before. And the cost, the volume times price gives you the cost. But the actual load, over forecasting and under forecasting, there were more load than forecasted. Okay, so the imbalance is we have this amount of energy deficit in this time period, right? And this amount should be purchased at the spot market at spot price. So these are the spot prices. So imbalance volume times spot price gives you the balancing cost. So minus is the profit, plus is the cost. Okay. So total hourly cost is the forward purchase cost plus balancing cost. Right? This plus that gives you that number. This plus this gives you this number, right? And hourly revenue is the actual load times the flat rate, $37 in this case. So this times 37 gives you this. Am I correct? 아닌 것 같은데. 203 times 37 gives you, what am I talking about? Hourly revenue. So yeah, this times that gives you this number. 삼, 7에 21, 2, 7에 14, 9, 115 맞잖아. Yeah, it's correct. Okay. So revenue minus this cost gives you this number. Okay, everything else is same. 설마 지금 이걸 보고 있는 건 아니겠죠? You are not looking at this. Okay. Any questions so far? Yeah, so we discussed consumers' perspective and retailers' perspective, and let's move on to generators' perspective. Actually, no. We will first talk about an ideal case. Ideal case means a simple case. That is the perfect competition. Okay? But when there is so perfect competition assumes a lot of producers and a lot of buyers. But as the number of producers, as the number of generators decreases, we go to oligopoly market. And if there is only two companies, that is called duopoly. And if there is only one company, that is called monopoly. So, in the case of monopoly, monopolist sets the price at will. So that's why we need to have a regulator, non-profit regulator run by government. And the extreme opposite case is perfect competition. So here we assume that no participant is large enough to affect the price. So the price is just determined at the market equilibrium, and no single producers or consumers can affect the price. Okay, that means all participants act as price takers. Okay, so price takers means you just take the price. You cannot affect the price at all because you are so small. Then what is the opposite word of price taker? Price giver. Price maker, yeah, that's better. Not price giver. Yeah, the opposite of taking is giving, but no. Price maker or price anticipator. Okay, price anticipation or price make, no, they have same meaning. So, monopoly, duopoly, oligopoly, the players are not at all price takers. They are price anticipators. So they want to change the price so that they can have more profit. Okay, so in the case of oligopoly markets, some participants are large enough to affect the price. So they want to have a strategy, the bidding strategy, and they want to have some market power. Market power means if you have more market power, then that implies you can change the price more easily than others by changing the quantity you are producing. Okay? Actually, in the second half part of this chapter, we'll talk about the game theoretic perspective in this oligopoly market. Okay? So, so in this oligopoly market, some are price anticipators and some are just price takers. So there is a concept of leader and followers. Okay, so leaders are price anticipators and followers are price takers. We will visit that shortly. So let's talk about this perfect competition case. So all producers have a small share of the market. Similarly, all consumers have a small share of the market. So single entity cannot affect the price. So individual actions have no effect on the market price. Okay, so all participants are price takers. So in this case, analysis is relatively easy, and we want to focus on short-run profit maximization from a price taker's perspective. So you remember the concept short-run versus long-run. Okay? So in short-run case, we ignore the fixed cost. We only focus on the operational cost. Okay? This fixed cost must be compensated later anyway, but for the simplicity of analysis, we focus on the short run, ignoring the fixed cost. So suppose that Y is the output of the generating company, and pi is the market price. This is determined from the market. It is independent of the amount of production quantity of the company. Okay, so pi is just constant here. This is not a function of Y. So the revenue is pi times Y, and the cost is denoted by C of Y. This cost comes from the generating cost of the energy. So now what you want to do is, given market price, how much I need to produce. I want to determine the quantity Y to maximize my profit, right? So revenue minus cost. So take the derivative. This with respect to Y gives you pi is constant. This is independent of Y. So this gives you this simple equation. So you need to increase your production level up to the point where your marginal cost is equal to the market price, right? Yeah. If your marginal cost is smaller than the market price, you'd better produce one more unit and sell it to the market. You can sell it because the market is huge enough. So there is a guy who wants to buy that from you.
근데 아까 올리고폴리 같은 경우는 몇몇 참여자가 가격을 영향을 줄 수 있다 했는데 그럴 경우에는 파이가 Y에 대한 함수가 될 수도 있는 건가요?
Yeah, good point. That's the case. So in the case of oligopoly market, pi is not independent of Y anymore. So of course, pi is a function of Y, can be a function of Y. So we will discuss two models, Bertland model and another model. And let's talk about that later. Kruno model and Bertland model. Okay. So adjust production Y until the marginal cost of production is equal to the price pi. So here is an example. A core-fired unit with minimum output 100 megawatt and maximum output 500 megawatt. This is the amount of fuel required to produce the power P1. Not fuel, yeah, coal. Core-fired generators, gas-fired generators. What else? Anyway, yeah, this is core-fired generators. And so F is the dollar per blah. So yeah, this is the amount of core, and this is the unit price, and so the unit price is $1.3 per blah. So this is the cost to produce power P1. Yeah, typically this is a quadratic function, a fixed cost. We have fixed cost here. And this serves as a marginal cost, mainly. And we have another term here. So when you look at this, this marginal cost is a linear function, right? And when the market price is $12, the amount you want to produce is determined by solving this equation, and that is this much, 257.7 megawatt. And this is within this minimum and maximum range. So this will be your generation quantity. Okay. So, but we need to think about unit limits, the maximum generation capacity and the minimum generation capacity. Optimization would be easy if we do not have constraints. But obviously, we have many constraints. So all the interesting things and all the bad things happen at the constraints. So suppose that at the maximum power level, the marginal cost is less than the market price. What should be your choice? Do you understand my question? 경영? Do you understand my question? Not really? 한 번만 다시. Okay. So Pi max is your maximum capacity. P, I mean, is your minimum capacity. When you turn on your generator, this is the limits, two limits. And the marginal cost at your maximum capacity is less than the market price. Then what should be your choice of running the generator?
Pmax까지.
Yeah, you should operate at this maximum power, because by producing power, you can earn money, right? What about this? If the marginal cost at your minimum power level is greater than the market price, what should you do?
시장에 참여를 안 하는.
Actually, you have two options. Do not participate in the market at all. Yeah, that's a clever choice. Second option is produce just a minimum at the minimum power level. So if we ignore the fixed cost, or if we ignore the startup cost, then in this case, you do not need to participate in the market. But if you consider the startup cost, and then maybe you'd better stay in the market during this time period, even though there are some loss. But after time goes on, the load increases, so you can sell more, and this price goes up. So rather than turn off and turning on your generator, you'd better just stay in the market, okay, and looking for a better time. So actually, we saw the power generator 2 days ago. Not real generator, but the augmented reality, virtual reality. That looks fancy. Anyway, there's a turbine. There's a mechanical machine, and turning on and turning off this mechanical machine gives a lot stress on the parts of the machine. Okay, so turning on and turning off are not that kind of easy job as you think. Okay, so typically for easy analysis, we have this kind of quadratic cost function, but this can be simply modeled using this linearized cost curve, piecewise linear cost curve. So this is the output power of the generator, and this is cost function. So this is not a quadratic function, but a piecewise linear function. And these points are called breakpoints or elbow points. So, okay, why do you think a generation company have this kind of, how they can have this kind of piecewise linear cost curves? Well, maybe they have several units with different marginal cost. Okay, so unit 1, 2, 3, they are combined, and this is the combined output of a single company. That can be possible. So this is the cost function, and this is the marginal cost. So up to constant marginal cost, another constant marginal cost, another constant marginal cost. And these are the break points. Okay, so let's think about this patch with piecewise curves. And here, what is I? This I is the generating company index. But anyway, we are only focusing on a single company, so this index I does not change at all. And marginal cost 1, 2, 3. So marginal cost 1, 2, 3. And then the minimum and maximum and 2 elbow break elbow. Break points or elbow points. Break elbow is break your elbow, so not a good words. Don't break your elbow. Okay. So When the market price is lower than MC1, then yeah, you just stay. You decide to stay in the market. So your generation power is kept at the minimum. And when this pi is greater than marginal cost 1, that is here, maybe somewhere here, then the intersection is this much. So you need to generate up to the maximum point of this period. So E1, that should be, yeah, the output power should be E1. No, and same thing happens. Example. So these are the market price, and this is the generation amounts you choose. And so okay, we 100, 500, 250, 400. Those numbers are, yeah, so suppose that this is 100 and 250 and 400 and 500. Yeah. And the linearized piecewise linear cost curve is like that. So these are the marginal cost. So depending on the market price, if the market price is less than 11.57, no, the generation quantity is kept at its minimum level. So that is 100. So 100. After that, up to this point, yeah, 12.35, the generation quantity should be 250, right? So that is here. And if the price is higher, market price is higher than 12.35, then this guy need to generate at its maximum 400. So that's why 400 up to $13. Okay. And if the market price is higher than $13, generate at its maximum power 500. Yeah. That's it. Any questions so far? So based on this curve and based on the cost curve and based on the amount of generation, you can compute the cost and you can compute the revenue. So revenue minus cost give you this profit curve. Profit versus the market price. So we will get this kind of curve. So what does this curve, so what kind of information does this curve give you? Suppose that you are an operator and you have this analysis. Yeah, this is the market price, and I know my generator, the cost curve. So this is the profit. And actually, this market price changes over time, right? So this is determined in the market. So when you have this curve and when you have a distribution of price, you can compute your expected profit, right? Okay. So we looked at a simple example, and actually when you have a generator, you need to schedule the output power considering these things, the startup cost. So far I didn't discuss startup cost much, but because we have the startup cost, even if for some period we cannot make money, we need to stay in the market. and the operating constraints, the minimum and maximum power generation limits, and also the turning on and turning off cost. So you may think turning off does not harm your machine, but that's not true. Both turning on and off can stress the machine. It can damage the machine mechanically. So that should be limited. Okay? That is the operating constraint. Maximum power generation, minimum power generation, and also when it's turned on, it needs to be run at least this amount of time. When it's turned off, it needs to be in the idle mode for this amount of time. Okay? They are operating constraints. Environmental constraints. No. Because of these environmental constraints, the coal-fired plants are not welcomed these days. By contrast, LNG, natural liquid gas, that's expensive, but that's kind of clean energy. And other revenue opportunities. What does this mean? So, as a generating company like Komipo, you visited. So, as a generating company, you sell energy and get paid dollar per megawatt hour, right? But they can seek another types of revenue opportunities, not by selling energy. There are another types of revenue source. We will discuss that maybe in chapter 6, but collectively they are called ancillary service. I think ancillary service. So I think I talked about this before. So this includes frequency regulation, voltage regulation. What else? Reserve power, blah, blah, blah. So all of these things is to maintain the grid stability. Okay, so far we assume that by selling energy, megawatt hour, the generator can get paid. But sometimes they can get paid even if they do not provide any energy, but just provide their capability of providing energy. You don't know what I'm saying. Okay, so yeah, those topics will be covered here. Okay, this is about frequency regulation, voltage regulation, and the reserving power. And the main idea is this: from ISO perspective, independent system operators perspective, they want to make sure that this supply and demand are matched all the time, right? So they want to make sure that I have enough capacity to provide to meet the total demand. So as a generating company, you say, hey, I can provide 100 megawatt for 1 hour. I have that capability. So by guaranteeing that, they can get paid. Of course, if they cannot fulfill their commitment, they need to pay a lot of penalty. Okay? But anyway, even if they do not provide any real energy on that time period, but just preparing these generation units to provide power in emergency case, they can get paid. Okay? So that is called the reserve power. Okay, and also this forecasting error affects the profits and revenue of the company. Okay, so this is an example. For 7 time slots, for 7 hours, this is the price. This is generation amount. So this is this times that give you this revenue, and this is the running cost of the generators, and startup cost occurred here. Turn on the generator, but the generator keeps running, so no more startup cost here. Total cost is running cost plus startup cost. Give you this number, and the profit is revenue minus cost, gives you that. So the cumulative profit, the sum of this and that gives that, sum of this and this gives you that, So this is the cumulative profit. Anyway, they can make money here. Any questions? So far, so good? Okay. And let's think about the generator's perspective further. And here we are focusing on a company, a generating company, and this generating company has n number of units. Okay, so they want to minimize the total generation cost, and so this generation company committed to deliver this amount of power, L. So the sum of the power should be equal to L. So this is the constraint of the company. So this company obviously wants to minimize the total cost to deliver L amount of power. So actually, no, this is a standard, easy optimization problem and convex optimization problem, because this is quadratic function. Right? So we have a convex optimization function, convex objective function, and single equality constraint. Then the question is, how can we determine PI that minimizes the total cost and satisfying this single constraint? So we need to construct Lagrangian or Lagrange function. So cost plus the equality constraint, and this lambda is a Lagrange multiplier. And my question is, maybe you are confused whether I need to put plus here or minus there. So why is it plus here? Well, actually, this is L minus that, so this is plus. But if this is sigma minus L, then this should be minus. But we select plus here because lambda is kind of price, and it would be better to keep this price positive. So anyway, so why does it look like that? My question is, what about putting minus here? Why it is plus lambda, not minus lambda? Yeah, of course you can put minus here. You can put minus here. Then instead of lambda, you have all other places. Lambda should be replaced by minus lambda, but physically that's not good. So I'm asking you, how can you determine the sign in front of this Lagrange multiplier? How can you do that? 민재. 정답은 오늘 오후 4시 반 SHS 개론에서 만나요. Hey, tell me, how can you determine the sign here, plus or minus?
PI 마이너스 L이 아니라 1 빼기 시그마 PI에서 마이너스 람다를 플러스 람다를 바꾸는.
뭐 같은 얘기죠, 그거는 뭐. So, okay, you have two options: the sign here and the order. Okay, so L minus summation blah or summation minus L, and the sign. Actually, they are connected. How can you determine one from other?
해야 되는 게 미니마이징일까?
Yeah, even if you put minus sign here, everything is okay. So, yeah, the sign is always confusing if you do not perfectly understand. So, so according to Professor Boyd, convex optimization is minimize of objective function subject to we always put constraint in this way. Okay? So for convex optimization, this is convex function. This is convex function. This is affine function, right? And then the way actually this is equality constraint. So well, either is fine, yeah, right? But to have a better intuition, it would be better to say, instead of that equality constraint, if you want to change this optimization problem having inequality constraint, which direction you need to put inequality sign? Greater than or less than? To have the same solution. The sum of the generation should be greater than or equal to this load, right? So you have summation pi should be greater than L. This should be your constraint, right? And then from that, what you have is L minus summation I pi should be less than 0. Same constraint. And then, in this standard notation, you know that the Lagrangian function is objective function plus Lagrangian multiplier times fix, right? So in this case, we put plus sign here, and the Lagrangian multiplier for inequality constraint is non-negative, always. Okay, so that's why we have this term here and lambda and plus. Okay, so anyway, after you formulate the problem as a mathematical optimization problem, then the next step is straightforward. Take the derivative of this Lagrangian function with respect to a variable and the Lagrangian multiplier, and the derivative must be 0 at the optimal point. So the gradient L with respect to P should be 0. And the gradient of this with respect to lambda should be 0. So that's where we have this constraint part. And this is about the key point here is that the generation power of unit I can be expressed by a single parameter lambda, right? From these equality constraints, not equality constraint, from this equation. So yeah, they are all same for all I. So we have this term. So all generation units must have the equal marginal cost, and the equal marginal cost should be equal to another variable lambda. So this variable lambda is called dual variable, as you know. Okay, so that's it. So here, what this company determines is that, yeah, the P1 and P2 Pn that satisfies this equation is the optimal generation quantity. And this lambda is something. So this lambda is called shadow price. And okay, by the way, this lambda is not necessarily same to the market clearing price. This is just come from the optimization, right? And then you need to think about what is the relationship with this and the market price, pi. What is the implication of that? Anyway, this is just the solution of this optimization problem, and there will be a market price. Then, depending on the market price, you need to do something, and what should be the next job? Did you understand my question?
람다를 마켓 플러스보다 낮게.
You cannot change lambda on your own. So this optimization problem says that you are a generation company. You are committed to deliver this amount of power, and to generate this amount of power, you need to produce P1, P2, that satisfy this one. And lambda is something. Lambda is what? Lambda is the marginal cost of all the units. So what it says is, if this lambda is greater than, if this pi is greater than lambda, your marginal cost is less than the market price, right? So you can make profit. The opposite case, you lose money. Simply. Then you may think, hey, I don't want to produce power. I don't want to sell my energy because I cannot make money. But here the assumption is that you are committed to deliver power, and the amount is L. Okay. So let's look at a simple example. So the generation company has two generating units, A and B, and these are the cost function and that are the cost function, and the delivery amount is 260. So that we have this Lagrangian, take the derivative with respect to PA, with respect to PB, so this and that. So PA can be expressed by lambda, PB can be expressed by lambda, and using these constraints, PA plus PB should be equal to 260, and that gives you PA that, PB that, and this sum of these two is 260, and this is the shadow price. Okay, so if this is less than the market price, you can make money, and vice versa. Okay, so under this circumstance, we can think of, hey, you are a generation company, and suppose that this is a perfect competition. So there is a market clearing price, and then I know my shadow price, my marginal generation cost. Then what should be your bidding strategy in the market? This next question. You understand my question? Okay. So, if you bid at your marginal cost, the conclusion is that's good. Okay. And if you bid less than your marginal cost, that's not good. If you bid more than your marginal cost, that's not good either. Okay, so bidding at the marginal cost all the time is the best strategy in this perfect competition. Okay, but let me stop here, and we will start from this page next Monday. Thank you.